Picture this. It's 2 in the morning. You open your refrigerator, grab a bottle of cold water, and close the door without a second thought. It feels completely, utterly ordinary. You expect the light to turn on, you expect the air to feel crisp, and you expect that water to be perfectly chilled. But, for most of human history, keeping food fresh was a monumentally difficult and honestly an incredibly expensive undertaking. Think about it. Our ancestors had to rely on extreme measures just to stop their next meal from rotting. You'd have to salt your meats heavily, bury your root vegetables deep in the soil or in snowdrifts, or, if you were wealthy enough, have massive blocks of ice literally carved from frozen lakes and shipped halfway across the world by train and boat, all just to keep a beverage cool in the summer. Today, we don't even give it a second thought.
Yet, right there, inside that mundane metal box, one of the greatest engineering inventions of modern life is quietly and tirelessly moving heat, every single second of every single day. We take this everyday magic completely for granted. From the outside, it's just a boring, humming appliance that holds our milk and leftovers. But behind that sterile white or stainless steel exterior lies an incredible story of physics and engineering. This metal box is actually a masterful, perfectly balanced thermodynamic engine hiding in plain sight right next to your kitchen sink. It's a relentless machine, quietly doing the heavy lifting of modern civilization. In this explainer, we're going to peel back the outer shell of this everyday object and explore the fascinating, continuous cycle that protects our food and fundamentally change the way humanity lives.
So the crucial question is, how exactly does it do this? How does a refrigerator actually keep things cold? It's a question that seems so simple on the surface, doesn't it? You plug it into the wall, a motor hums, and things get frosty. But the actual answer requires us to completely rethink how we understand temperature and physics. To truly grasp what's happening inside that humming box in your kitchen, we have to let go of everything our intuition tells us about what cold actually is. Prepare to have your perspective entirely flipped upside down. This completely shatters the biggest misconception we all carry around. When you open that door and feel the crisp chill on your face, your brain instinctively tells you that the refrigerator is somehow creating cold air and pumping it into the box. But in reality, according to the laws of physics, you cannot create cold. Cold isn't a physical thing you can make or produce. It's simply the absence of heat. Heat is the actual measurable energy in the universe. So, your refrigerator isn't a machine that makes cold at all. Instead, it acts as a masterful, highly efficient heat thief. Its singular, relentless goal is to find heat energy hiding inside the box, capture it, and forcefully evict it into your kitchen. It's literally an eviction notice for heat. To pull off this endless heist, the refrigerator relies on a very special main character. Meet the refrigerant. Think of this specialized chemical fluid as a tireless, microscopic delivery worker. This worker's sole job, day in and day out, is to walk into the interior of your fridge, pick up an armful of heat energy from your leftover pizza and your orange juice, carry that heat outside the box, drop it off in your kitchen, and then go right back inside for another load. Historically, the early versions of these delivery workers were incredibly volatile. We used gases like ammonia, methyl chloride, or sulfur dioxide. And while they moved heat efficiently, they were toxic and sometimes highly flammable or corrosive if they leaked. A leak could literally mean a fatal disaster in the home. Today, we use much safer, heavily engineered synthetic fluids, but their fundamental job remains exactly the same: absorb, carry, and remove heat. The mechanical cast consists of 4 main parts that make this continuous cycle work: the compressor, the condenser, the expansion valve, and the evaporator. You can track the journey of the refrigerant as it constantly moves through these 4 beautifully engineered components, entirely sealed off from the outside world. As it travels, the refrigerant is forced to change its physical state from a liquid to a gas, and then back to a liquid again. By physically manipulating the pressure of this fluid at these 4 specific checkpoints, the system forces the refrigerant to absorb heat in one place and release it in another. Let's move to the first component and see how this brilliant cycle actually begins. Step 1. The compressor. Squeezing the heat. Usually located at the very bottom back of the fridge, this heavy metal motor is the beating heart of the system. The compressor takes low-pressure refrigerant vapor that's just absorbed heat from inside the fridge, and it violently squeezes it. Imagine a crowded subway car at rush hour on a sweltering summer day. If you take all those people, or in this case, all that vibrating heat energy, and you forcefully pack them tightly together into a much smaller confined space, things are going to get very, very hot. By mechanically compressing the gas, the compressor forces the heat molecules so incredibly close together that the refrigerant becomes a superheated, high-pressure vapor. It's squeezing the heat so intensely that the vapor inside those pipes becomes significantly hotter than the room temperature air sitting in your kitchen. Which brings us to a fascinating curiosity loop you've probably experienced firsthand. Have you ever dropped a pen or a piece of mail behind your refrigerator, reached your hand back there into the dusty gap to grab it, and noticed that the air behind the appliance is surprisingly, almost uncomfortably warm? Think about that for a second. If the entire purpose of this massive machine is to keep things freezing cold on the inside, why is it generating so much physical warmth on the outside? Where is all that heat coming from, and why is it blowing onto your kitchen floor? Step 2. The condenser. Dropping off the heat. That warmth you feel is exactly the condenser doing its job. After the compressor violently squeezes the vapor and makes it superheated, that highly pressurized hot gas travels through the condenser coils. These are those winding, serpentine black tubes or wire grids you often see exposed on the back or hidden underneath the bottom of the fridge. Because the superheated gas inside the tubes is now much hotter than the ambient air in your kitchen, the fundamental laws of thermodynamics take over. Heat always, universally, flows from hotter areas to colder areas. So the heat simply radiates out of the metal tubes and into your room's air. As the refrigerant drops off this heat, it cools down just enough to liquefy, condensing back into a high-pressure liquid. Our tiny delivery worker has successfully dropped off the package of heat. Step 3. The expansion valve. The rapid cool down. But now we have a serious problem. The refrigerant is a liquid, and it's outside the fridge, but it's not cold enough yet to go back inside and actually cool your food. Enter the expansion valve, often called a capillary tube. This is simply a tiny, pinhole-sized restriction in the copper tubing. The high-pressure liquid is brutally forced through this incredibly narrow needle hole into a much wider, lower-pressure environment on the other side. This sudden, violent drop in pressure causes a rapid and explosive flash evaporation. The fluid violently expands in a fraction of a second. A portion of the liquid instantly turns into a gas, and in doing so, it forces the entire remaining mixture to experience a massive, shocking plunge in temperature. To understand why this violent expansion works so perfectly, just think about an everyday spray paint can, or one of those cans of compressed air you use to blow the dust out of a computer keyboard. When you hold down the nozzle and let the highly pressurized liquid contents violently expand and escape into the lower pressure of the room, what happens? The can instantly gets ice cold in your hand. Sometimes it even forms literal frost on the metal. Changing pressure changes temperature. The expansion valve does exactly this, but on a continuous, controlled loop perfectly sealed inside the copper piping. By instantly dropping the pressure, the expansion valve turns our refrigerant into a freezing cold, partially vaporized mist, perfectly prepped for its most important job yet. Step 4. The evaporator. Stealing the heat? Now we're finally back inside the cold box. This freezing mist flows through the evaporator coils, which are cleverly hidden behind the interior walls of your freezer and fridge. A small internal fan quietly blows the air from the main compartment over these freezing coils. Because the refrigerant mist is now vastly colder than your leftovers, it effortlessly steals the latent heat right out of the food. Think about a warm leftover slice of pizza sitting on a shelf. The heat energy vibrating inside that pizza radiates out into the air of the fridge and is then immediately pulled into the freezing metal coils. As it absorbs this heat energy from your food, the freezing liquid refrigerant completely boils and vaporizes into a gas. It essentially uses the stolen heat from your pizza to fuel its own evaporation. The newly chilled, heat-depleted air is then blown back into the main compartment, keeping your milk cold and your lettuce perfectly crisp. And then the entire cycle continues without a moment's rest. That slightly warmed, low-pressure vapor, now carrying the heat stolen from your pizza and your milk, leaves the evaporator coils and gets sucked right back down into the compressor motor, to be violently squeezed again, starting the entire tireless journey completely over. Squeeze the heat to concentrate it, drop it off outside into the kitchen, flash freeze it through the expansion valve, and send it back inside to steal more heat. Over and over, millions of times a year, day and night, all happening silently in the background while you sleep. It's a perfectly choreographed dance of thermodynamics that never takes a day off, relentlessly guarding the safety of your food. But this delicate, perfectly balanced, continuous loop of physics faces one major, deeply unpredictable adversary: us. Human behavior. What happens to this beautifully engineered thermodynamic ecosystem when you walk up, yank open the heavy door, and just stand there bathed in the light for 2 solid minutes, staring blankly, trying to decide if you want a handful of grapes or a piece of cheese? We've all done it. But from a strict engineering perspective, opening that door is basically like setting off a thermodynamic bomb inside the carefully controlled appliance. This brings us to what engineers affectionately call the door problem. You see, cold air is physically denser and significantly heavier than warm air. When you swing open the door of a standard upright refrigerator, you break the seal.
Instantly, all that heavy, carefully chilled cold air literally falls right out of the bottom of the fridge, cascading down and spilling over your feet onto the kitchen floor. In that same exact second, warm, humid room air from your kitchen rushes right into the box to fill the vacuum left behind. In just a few careless seconds, you've completely erased hours of hard work by the cooling cycle. This physical reality is actually why chest freezers, the big horizontal ones that open from the top, are vastly more energy efficient. When you open the lid of a chest freezer, the heavy cold air just sits safely at the bottom, perfectly contained like water in a bathtub. But with an upright fridge, all the cold is lost, and the system must suddenly work much harder to recover.
Because of these constant, chaotic temperature fluctuations caused by us endlessly opening the door or simply adding a giant batch of hot soup leftovers, the refrigerator cannot just run continuously at one steady, efficient speed. It relies on a delicate thermostat to constantly monitor the interior climate. When the temperature creeps up past the danger zone, the thermostat triggers a switch and clicks the compressor on. We all know that distinct auditory cue when the house is totally quiet. You hear a sudden deep click, followed instantly by the low, vibrating hum of the heavy motor kicking into gear. The fridge runs in short, repeated cooling cycles, sprinting to steal enough heat to get the interior temperature back down to the target, and then abruptly shutting off to wait until it's needed again. It's a never-ending game of thermodynamic catch-up. And what is truly mind-blowing about all of this is the sheer monumental scale of this technology. This exact same heat-stealing magic, the compressor squeezing, the condenser dropping off, the expansion valve chilling, and the evaporator stealing, it isn't just used to keep your groceries safe. It's the exact same fundamental science used in air conditioners. That heavy box hanging out of your bedroom window or the massive unit sitting next to your house is quite literally just a refrigerator turned inside out. We're just using a much larger system to steal heat from the air inside your living room and aggressively dump it outside into your yard. In fact, it's estimated that roughly 5% of all electrical energy used in United States homes goes solely toward powering these specific cooling cycles. 5% of our massive residential power grid is dedicated just to moving heat from one place to another using this exact same four-step cycle. Which brings us to this final, incredible thought. The next time you grab that cold bottle of water in the quiet darkness of the middle of the night, take a slow second to listen to the gentle, low hum of the compressor motor vibrating against the floor. Remember that you are not just looking at a mundane metal box. You are standing in front of a relentless, finely tuned thermodynamic engine that changed the course of human history. Your refrigerator doesn't make cold. It quietly steals heat, protecting your food every second of every day. It's an engineering marvel hiding in plain sight. Thank you so much for joining me on this explainer, and keep looking for the absolute wonder in the ordinary things around you.